Okay, I'm going to post these in numerical order. So the first one is the 6.3 economic lot size, order quantity, and elasticity. So this formula comes from calculus, but we're not going to talk about the calculus that leads to it, so you're just going to use it. And the main thing is to remember what all these letters stand for. Q stands for the number of units in a batch. K is the cost of storing 1 unit for 1 year. Little f is the fixed setup cost, and M is the number of units produced total. So if you take the total number of units produced total per year and you divide by the number of units per batch, then you get the number of batches. Okay, so we'll look at, I'm going to go ahead and take this with me, and then we'll take this question over. I have carpet being installed, so that's what that is. Okay, so suppose 100,000 lamps are to be manufactured annually. So the total number manufactured annually is capital N. And it costs $1 to store a lamp for a year. And it costs $500 to set it up. So the question is, what number of lamps should we produce per batch? So we're looking for Q. So Q equals so this is 1, 2, 3, 4, 5, 6, 7. Wait. Yeah. Okay, so 10,000. So that's the answer for A. Now we want to find the number of batches of lamps that should be manufactured. So we just found that we should have 10,000 in a batch. We know the total we produce is 100,000. So, and I don't even remember what I guess there wasn't a letter for this. So it was just M over Q. So 10. So we should have 10 batches of lamps manufactured annually. And keep that. Go to this one. Okay, so a paint company has a steady annual demand for 24,500 cans. Okay, the controller for the comptroller for the company said it costs $2 to store a can of paint for a year, and $500 to set it up. The number of cans per batch. Oh. Okay, so 3,500 is our Q. So the number of batches Okay, so now we still have this, but now we have a new question of before in those two we got an integer value. So if we don't get an integer value, then we need to get the integer, the next lowest integer, smaller than q. So if we get 24.3 number of units, then we make it 24. And we also need to look at the next larger one, so 25, and then we decide which one's going to save us money. So basically there's some sort of curve going on in between there, but it's not symmetric, so you can't just round. Even if it's 24.1, it might actually be cheaper to go with 25. So we plug it in now to this total cost. Okay. So we have okay, so with this result, I think it's almost certain it should be $48.99, right? Because that's like super crazy close to $48.99. But we need to plug it in just in case. So the things we need to check are 48.98 and 48.99. So we want FM 60. Oh, yeah, it's all there. So F times M divided by 48.98 plus K times 48.98 divided by 2. So we get that from 48.98. Now we'll try 48.99. So 60. Oops. So that's super, super close. So this one's just a little bit more. So the 48.99 saves us like this, not even a penny, but not even close to a penny, in fact. But anyway, the cheapest way it seems is 48 $1.99. So that would be our Q. All right, so now we're to actually a fairly valuable thing. So what's going on with elasticity of demand is we're comparing the percent change in demand with a percent change in price. So if demand changes faster than price, then what happens is that you're not bringing in as much revenue as you increase the price. So as you're increasing the price, the demand is of course decreasing, because that's what always happens, except in these kind of weird phenomena with the, like brands. But if the demand changes faster than price, then you're selling too many fewer for the increase in price. And this is in percent, so it's already kind of scaled. So that means that your revenue is decreasing. So if you increase the price, you're going to make less money. So percent change in demand is the change in quantity over the quantity times 100%. The change in price, percent change in price, is change in price divided by the price, because it's percent of price, also times 100%. So we can just drop the 100% in both cases and just make these proportions. And then this is just invert and multiply. And this is rearranged, because when you multiply fractions, of course, it's straight across. So this is just rearranged. So then, as the change in price is small, so we're looking at sort of a point, if I increase the price from this point, then that's actually the derivative. The limit is the change in P goes to 0 of change in Q over change in P. So this bit right here becomes dQdP. So what goes in this blank is dQdP. So they always have opposite signs, again, except in the weird cases with expensive brands. So we just put a negative sign so that elasticity is always positive. It's always going to come out negative, so we just change the sign. So we have P over Q times dQdP, and that's how you calculate elasticity, which again is just this, as the change in P goes to 0. Okay, so again, if the change in demand is higher, so this is changing faster than the change in price, that makes the elasticity greater than 1. If the elasticity is greater than 1, then as you increase the price, you lose more money. If, on the other hand, the price can increase faster than demand, then your revenue is going to increase, and that is called inelastic. So I'm raising the price, and it's not really changing the demand that much comparatively, so it's inelastic. Elastic means, highly changeable, basically. So the demand is highly changeable or elastic if it's changing faster than price. Unit elasticity, where the elasticity is 1, they're changing at the exact same rate. So then that's maximized. Your revenue is maximized, and as you increase the price, nothing happens to your revenue, that is. Okay, so find the elasticity of demand for the given demand function at the indicated values. We're going to determine if it's elastic, inelastic, or neither. All right. So this is Q. then the QDP is just -2. Okay, so the minus cancels out this minus, so I just put the 2, which would have been kind of over here in parentheses and shorter there. So this is P over 150 minus P. At 100, that's 2, which is greater than 1. So since this is greater than 1, the demand's changing faster than the price, so it's elastic. So as price increases, revenue decreases. Sorry, this looks crazy. I'm distracted by all these things happening. 50 over 150 minus 50, that's 0.5, less than 1. So that's inelastic. So at this point, if you increase price, you increase revenue. Now we wanted to know, where is revenue maximized? Well, remember that revenue is maximized when the elasticity is 1. Well, since I have the elasticity here, I'm just going to set it equal to 1. So what quantity will maximize revenue? Here we don't have quantity, we have price. So Q so 150 quantity maximizes revenue. Okay, so we want to plug in 20. Okay. Oh, wait. Yeah, that seems very large. Oh. Doing my arithmetic wrong. Okay, so 0.5, so that's less than 1. And less than 1 means that demand changes slower than price, so it is inelastic. So as price increases, revenue increases. Okay, so that's greater than 1. So that is elastic, which means as price increases, revenue decreases. Okay, so this is the last thing on this section. And then I'm going to go do more active things and then come back and do the next one. All right, so Q I'm changing this just to make it a power of P so that we can just take the derivative. That looks horrible. Alright, I ran over and got a calculator to do that. This is okay, so I have P times P to the 0.5314, which is P to the 1.534. Down here I have P to the 1.534. So these actually all cancel. And this I got from multiplying these two values. So this is 0.5314, which is less than 1. So because it's less than 1, it is inelastic. And so ends this unit.